Okay, welcome back. So let me continue what we were doing last time. We were doing an example with S3 and computing characters. So we were looking at defining representation, where S3 acts on it's acting on R3 using the usual permutation matrices, and basically this is just acting by permuting the coordinates of R3. And so we had this this character, which was chi, and we said let's write chi as M1 chi1, where we said this was the trivial character, and then we said plus M2 chi2, where chi2 is the character for the sign representation. And then there was this plus M3 chi3, where this is some other mysterious irreducible representation. And then we computed some inner products. So we said, well, when we computed the inner product of chi with chi1, we found that M1 had to be 1. We also found that M2 had to be 0. And then at the end, we were finding that M3 also had to be 1. So, so actually, this term disappeared, and these were just 1. So it's just chi1 plus chi3. And we can figure out what chi3 is explicitly because, well, we know what chi does explicitly. Because this is the defining representation that acts with permutation matrices, if you think about the trace of a permutation matrix, it's just the number of fixed points, right? I was saying, more generally, when you have a permutation representation, the trace is just giving you the number of elements fixed by some element of the group, right? So like chi of a permutation is just going to be the number of fixed points of that permutation. And chi1, okay, this is the trivial character, and it's just going to be 1 always. So chi3 of a permutation pi is just the number of fixed points of pi minus 1. So we could complete the character table for S3. So here we have the character table. And this was this square table where on the top we have the conjugacy classes. K1 was the, okay, maybe I'll write it as like the conjugacy class of just the identity. And then the second thing is going to be the conjugacy class containing the transpositions. So it would be like 1, 2, 1, 3, and 2, 3. And then the third conjugacy class has the 2, 3 cycles, 1, 2, 3, and 1, 3, 2. And then here we have the irreducible characters, which are chi1 for the trivial, chi2, which is sign, and then chi3, which is now this thing, which is the number of fixed points minus 1. And then we can just fill in what these are. These were all 1s. Chi2 just gives you the sign of the permutation, so the sign of the identity is 1. The sign of a transposition is negative 1, because remember the sign is like negative 1 to the power of the number of transpositions that you need in order to write that element. So if you have a transposition, you can write it as just 1 transposition, so it's negative 1 to the power of 1. And then 3 cycles can be written as a product of 2 transpositions, so that's negative 1 squared, which is 1. And then finally, for the last row, we say, okay, well, how many, if we take the identity permutation on S3, how many fixed points does it have? Well, 3, because it's fixing all the numbers 1, 2, and 3. So 3 minus 1, that gives us 2. If you take a transposition, how many fixed points does it have? Well, 1, because It's just the one number that is not involved in the transposition, like 1, 2 fixes the number 3. So this has 1 transposition, and then -1 we get 0. And then finally, a 3 cycle has no has no fixed points because it's just cycling all of the numbers, 1, 2, and 3. So 0 minus 1 is -1. Okay. So that's the character table for S3. So maybe I wanted to go back and mention one thing that I had sort of glossed over earlier, and that is why we have this fact that that like if we have a character psi, then so this is fact that I glossed over. That if we have this character psi, then psi of G inverse is the complex conjugate of psi of G. And this is basically because when we proved Maschke's theorem, so Maschke's theorem was saying that every representation of a finite group over the complex numbers is completely reducible, so you can break it up into these irreducible components. What we saw was that we constructed some inner product that was invariant under the action of the group. And if you use this inner product, it allows you to construct an orthonormal basis with respect to that inner product. And then when you have this orthonormal basis, every element of the group under the representation gets represented as a unitary matrix. So let me just write some words. So by the proof of Maschke's theorem, if we have some representation, there is a, say, G invariant inner product. And if you have this inner product, you can choose an orthonormal basis with respect to that inner product, and then for each element G in the group, let's say X is the representation, so X of G is some matrix represented using this orthonormal basis. It's going to be unitary. And unitary is meaning that well, if you take the inverse, that's equal to the conjugate transpose. So, okay, what this is saying is that X of G inverse is the transpose of X of G, which I'll write like that, and then the complex conjugate. So this is like the usual in linear algebra, you can take the conjugate transpose of a matrix. And, okay, so from this, if we take traces, I should also say that because X is a representation, X of G inverse is the same as X of G inverse. And so then if we take the traces, the trace of this is just going to be, let's say psi is the character psi of G inverse. And here the trace is going to be, well, okay, if you take the trace of the matrix when you've taken the conjugate transpose, that's just going to be the complex conjugate of the trace of X of G. Right, so this is, like the trace of this is just going to be psi of G conjugate. And so that's why these are the same. Okay, so anyway, yeah, I just wanted to mention that briefly, but now let me go back to what I was doing here. Okay, so we worked out this example. Okay, so the next thing I want to do is talk about the regular representation and the group algebra of our group G, and we're going to decompose that into irreducible representations, right? So like here we're saying, okay, we have some representation, we're going to decompose it. Let's do that with the regular representation. Okay, so let's say we have a group G, and remember C bracket G is the group algebra of our group G. So the elements here are formal linear formal linear combinations of elements of G with complex coefficients. So in particular, you can think of the elements of G as giving you a basis, like a linear basis of this space, if you think of this as a vector space. But it's not just a vector space because it's also an algebra, meaning you can multiply things. Okay, so let's let chi reg be the character of the regular representation. Well, okay, so we know that we can write, so let's take C bracket G and view it as a module. So it's a representation of G because each element acts by just left multiplication. And so we can think of this as a G module. And as a G module, because we have complete reducibility, we know it's going to decompose as a direct sum. So let's write it as, say, a direct sum over some I of m sub I vi. So this is just what I've been doing with arbitrary representations where we're decomposing it into a direct sum of irreducibles, but now I'm doing it with the regular representation. And so this is like the VIs, this is running over all of the different irreducible representations, or modules in this case. Okay, so what we know, if we want, so let's try to compute mi. We know that mi is, according to some result that I proved last time, this is going to be the inner product of chi reg with chi I. So here chi I is the character for vi. And we can write out what this actually is. This is just 1 over the size of the group, and then the sum over G in G of chi reg of G times chi I of G inverse. Okay. Okay, but we've computed what the character of the regular representation is. We did this, I think, last time, or maybe the time before, because we said, well, this is just a permutation representation, right? The regular representation is a permutation representation where it's like permuting the elements of the group. And so we just said, well, the character is given by the number of fixed points. And we said, if G is the identity, then everything in the group is fixed by multiplying by the identity. So then the number of fixed points is just the size of the group. So I'll just remind you here, chi reg of an element G is, well, if G is the identity, it's just the size of the group, because everything's fixed by multiplying by the identity. But if G is not the identity, then nothing gets fixed when you multiply by G. So then you get 0. Okay? This is something we stated before. And so now that makes this sum very easy, because if G is not the identity, we get 0 here, so that doesn't do it. It just kills that term. And then if G is the identity, we just get the size of G. So I can say, okay, there's only one term in this sum that survives, which is when G is the identity. So I get 1 over the size of G times the size of G times chi I of G inverse. Okay, and that's just chi I. Oh wait, sorry. Sorry, this should be the identity. Because it's the term where this is the identity. Okay, so this just becomes chi I of the identity. But we said that when you take a character and you evaluate it on the identity element, you just get the dimension of that representation. Right. So this is just going to be the dimension of VI. And again, that's just because when you take the representation applied to the identity, you just get the identity matrix of that size, of the size, the dimension, and then the trace of the identity matrix is just the dimension. Okay? So what this is saying is that the number of times that an irreducible representation, so this is some arbitrary irreducible representation, the number of times that it shows up inside of the regular representation is equal to its dimension. And in particular, that shows that every irreducible representation shows up at least once in the regular representation, because every irreducible representation has dimension at least 1, right? You're not going to have any MIs being 0 here, okay? Okay, so every irrep appears in the regular representation. And that also shows that there are only finitely many irreducible representations up to isomorphism, because, well, this is just a finite number of things, right? Because the group algebra is finite dimensional, so you can only decompose it into a finite number of irreducibles. Okay. Okay, so let me summarize this with a proposition. Okay, so the same setup as before. G is a finite group. We're going to decompose the group algebra in this way. And so then, okay, the proposition says, first of all, what I just wrote is MI is the dimension of VI. The second is coming from a result that we had before, where we said the sum of the MIs squared is equal to the dimension of this, okay, so yeah, well, okay, let me just write it this way. The sum over I of dimension of VI squared. Yeah, okay, yeah, it's a better way of saying this is equal to the size of G. Okay, why is this? This is just because you take the dimension here. The dimension of this space is equal to the size of G, because the elements of G form a linear basis. And then here I'm just saying, okay, the dimension of VI, well, it's equal to the dimension of VI, and the number of times it shows up is also the dimension of VI. So you get a term which is dimension squared, and you're summing over I. So this just follows immediately from this. Okay, and then the third part is maybe the one that requires the most thought. The number of irreducible representations up to isomorphism is equal to the number of conjugacy classes of G. And so in particular, 3 is telling us that character tables are actually square because, well, the number of columns is obviously the number of conjugacy classes, just by definition. And so then this is telling us that actually the number of rows is also the number of conjugacy classes. Okay? Okay, so for the proof, okay, 1 and 2 follow from I'll say above, but it's actually below. And then for 3, okay, so let's do 3 now. So if you remember, at one point we said that the number of irreps equals the dimension of the center of the endomorphism algebra of C bracket G. Okay, so let me unpack this because we did this maybe a week or a week and a half ago. I said that there was some theorem where I listed a bunch of properties when I decompose any representation. Like if I had any representation and I decompose it in this way, there were a bunch of properties. One of them said that the number of different irreducible representations appearing is equal to the dimension of the center of, well, I think I phrased it as the commutant algebra, but it's the same as the endomorphism algebra if you view it as a G module of that representation. So this fact here is just something that I said before, but applied to this particular representation. Okay? And I guess I'm using the fact that so what I should say here is that this dimension is equal to the number of irreducible representations appearing in this representation. But what I'm actually saying here is that all of them appear in this representation. So this is actually just the total number of irreducible representations. Okay? Okay. So now, what we want to do is say, okay, well, what is this? What is the endomorphism algebra of the group algebra? So these are going to be linear maps from the group algebra to itself that commute with the action of left multiplication by G. Okay, so let's try to unpack this. Actually, I'll give an example of something in this in the endomorphism algebra, and then we'll see that pretty much all of them look like that. Okay, so maybe I'll ask, okay, what is the endomorphism algebra of the group algebra? Well, let me construct something in this set. So if I have some element V in the group algebra, I'm going to define a map phi V, so phi sub V, and this is going to be a linear map from the group algebra to itself, so it's a linear endomorphism. And it's defined by right multiplication by V. So it's just defined by saying that phi V of some element, let's say W, in the group algebra, this is just going to be WV, because V and W are both elements of the group algebra, and it's an algebra, so you can multiply things. So I'm just multiplying. Okay? But there's this very nice fact, which is an obvious fact, but it's nice, which is that left multiplication commutes with right multiplication. If I right multiply by V, and then I left multiply by some other thing, that's the same as left multiplying by that other thing, and then right multiplying by V. So that's basically saying that this phi V is going to commute with the action of G, which is left multiplication. Right, so I'm just saying, so for G in G, if we take G times phi V of W, okay, well that's just G times WV, but that's the same as phi V of GW, right, that's GW times V, and so this is just saying that phi V commutes with the action of the group, so it's actually in this endomorphism algebra. So phi V is in the endomorphism algebra. Okay, and then the claim is that actually these are all of the elements of the endomorphism algebra. So what I want to claim is that, the map that sends an element V, so the map from C bracket, okay, I'll write it this way, sorry. The map sending V to phi V is an isomorphism from the group algebra to the endomorphism algebra of the group algebra. Okay, so it's a little confusing, I guess, when you say it, but it turns out that like the endomorphism algebra of the group algebra is isomorphic to the group algebra. And this is the explicit isomorphism. So how do we verify that this is an isomorphism? Okay, well you can check that it's a linear map, right? And you can check, yeah, so like, you can just write down that it's a linear map, that's fine. You can check that it is an algebra homomorphism, in the sense that like, if I had, I don't know, V times V prime, that would get mapped to phi sub V times V prime, but this is the same as like phi sub V, oh maybe it's an maybe it's an anti-isomorphism, I think that's what I want to say. Okay, so I'm going to put that there. Because, okay, it's actually going to reverse, so anti-isomorphism means that it reverses the order of multiplication. Okay, so V prime gets mapped to phi sub V prime, but this is the same as phi sub V prime composed with phi sub V, right? Because if I like multiply on the right by V prime, that's the same as multiplying on the right by V and then multiplying on the right by V prime. Okay, but this is fine. I mean, this is saying that like they're basically the same structure. It just reverses the order of multiplication. Okay, so again, it's a linear map, and this shows that it reverses preserves the multiplication, except it reverses the order. Now we just need to show that it's actually a bijection. So it's a linear map, so we just need to show that the kernel is trivial and that it's it's surjective. So okay, let me go over here, I guess. Okay, so for injectivity, okay, well let's suppose that some v maps to 0, which is saying that phi v is 0. So, okay, suppose phi v is the 0 map. Okay, well what that means is that if we take some w in the group algebra, we have that 0 should be equal to phi v of w, which is just w v. But since this is true for every, maybe I want to say, well, okay, this is true for any w. Let's take just the identity element of the group, right? So take the identity element of G, which is also viewed as an element of the group algebra, and then apply this. So you get E times V, okay, but that's the same as V. So this is saying, right, the only thing that maps to 0 under this map here, this thing, is 0. Okay, so that's injectivity, because the kernel is trivial. Now for surjectivity, let's just suppose we have some element theta in the endomorphism algebra. Okay, and we're gonna let V be theta of the identity. And the hope is that theta is going to actually be phi sub V. Okay, so why is this? Well, okay, for any G in G, we can compute that theta of G, right? So theta is a map from the group algebra to itself. So I'm viewing G as an element of the group algebra and applying theta to it. Well, this should be the same as theta of G times the identity, obviously. But then this is supposed to be commuting with the action of G, and you can think of this as like G is acting on the identity by multiplying on the left. So again, because theta is an endomorphism that commutes with the action of G, I should be able to pull the G out. But then theta V is this V. So this is saying that for any element of the group, theta just acts by multiplying on the right by V. And then if you just extend by linearity, the same is true if you started with some element of the group algebra. So extending by linearity, we find that the same is true for all elements in the group algebra, not just in the group. And then, okay, well that's just saying that theta is actually just what we were calling phi sub V. It's the it's the right multiplication by V matrix. Okay. Okay, so what have we done so far? Well, okay, now we know that the endomorphism algebra, sorry, earlier I was saying is isomorphic to, I should say it's anti-isomorphic to the group algebra, because this is an anti-isomorphism. But the dimension of the center doesn't really change if you do an anti-isomorphism, because like being in the center means that you commute with everything. Like this, the center of this endomorphism algebra is the set of things in the endomorphism algebra that commute with everything. But like commuting with everything doesn't really matter if you switch the, it doesn't change if you reverse the order of multiplication. So really this is the same, this dimension is the same as the dimension of the center of the group algebra itself. So what we've shown is, okay, the dimension of the center of the endomorphism algebra of the group algebra is equal to the dimension of the center of the group algebra itself. Okay? And again, this is just because this thing and this thing are anti-isomorphic. Okay, but now, well, now we have to figure out what the center of the group algebra looks like. So let's do that. Okay, so now, okay, what is the center of the group algebra? Okay, well, let's say we had some element of the center of the group algebra. Well, in particular, it's in the group algebra, so it's some formal linear combination of elements of the group. So let's say, suppose we have some element, let's say, Z. Okay, so let's say Z is in the center of the group algebra. And since it's in the group algebra, we can write Z in the form C1, G1 plus dot dot plus C in G in. And let's just assume that this is like going over the whole group. So some of the C's could be 0, but that's fine. Where G1 through Gn is just the entire group. And the coefficients are some complex numbers. Okay, so now, let's say we take some other element of the group H. So take some H in G. And let's conjugate Z by H. So first of all, okay, I should write ZH equals HZ. And here I'm thinking of H as an element of the group algebra as well. And this is because Z commutes with everything in the group algebra, because it's in the center. So another way of writing this, I can just write it as Z equals HZ H inverse. I just multiplied by H inverse on the right. And now let's just expand out what this looks like when we write Z in this form. So what this is saying is Z is this thing. C1 G1 plus dot dot plus C in G in equals Okay, so if I conjugate this by h, that's just going to conjugate each individual term by h. So I'm just going to get C1 H G1 H inverse, that's this term conjugated by H, plus, okay, and then all the other terms, and I get this one, C in H G in H inverse. Okay? So let's see what we can deduce from this, because here this is some linear combination of the elements of G, which are a basis for the group algebra. So if I'm just thinking of the group algebra as like a vector space, like this is a bunch of, it's a linear combination of a bunch of linearly independent things. And this will also be, I mean here as G1 through Gn ranges over the elements of the group, the conjugates by H also range over the same elements. So this is also just a linear combination of linearly independent things. And if you have two different linearly independent, or if you have two different linear combinations of linearly independent things, then the corresponding coefficients have to match, right? So what this is saying is that, for example, here the coefficient of G1 is C1, and over here, one of these terms is going to be G1, and its coefficient also needs to be C1. So like, so if, okay, let's say if, say G sub k is equal to H inverse G1 H, right? So let's just define G sub k to be the element that you get by multiplying, by conjugating by G1 by H inverse in this way. Then if I look over here, the coefficient of H GK H inverse on the right-hand side of this. Okay, well H GK H inverse is the same as G1. Right, so this is just G1. But okay, so the coefficient on the right-hand side is CK. Right, just because of the way that I wrote this. The coefficient of this thing on this side is CK. But this element is G1, so that coefficient needs to be the same as the coefficient of G1 on the left-hand side, which is C1. Okay, but this must equal the coefficient of G1 on the left-hand side, which is C1. Okay? So what I've done is I've chosen some arbitrary element of the group and said, okay, let's conjugate G1 by, or I guess the inverse of that element. So this is just, I mean, since H was arbitrary, this is just GK is some arbitrary conjugate of G1. And I'm saying that whatever this arbitrary conjugate is, its coefficient in this expansion, which is CK, has to be the same as the coefficient of G1. Okay, and then like there's nothing special about G1 here. We could have done this with G2 or G3 or whatever, and H can be arbitrary. So what this is really showing is that if you take any two elements over here that are conjugate, their coefficients have to be the same. Okay? So what this shows is that I have any elements, let's say gi and gj are conjugate, their coefficients ci and cj are equal. Okay? And that means that this element can be written as a linear combination of elements that are constant on conjugacy classes. Okay, so really, we can write z, this element of the center, as some summation of, let's say, di, let's call it zi, I equals 1 to k, where these are some scalars, and zi is just the sum of some conjugacy class. It's like sum over g in k. Okay, maybe I'll write it this way. Let's write it as sum over conjugacy classes k of dk zk. I kind of like this better, where each dk is some scalar, and zk is just the sum of the elements of that conjugacy class viewed as an element of the group algebra. Okay. Now, actually, okay, so any element of the center of the group algebra has to look like this, but you can check that any element that looks like this is also in the center. To do that, it just suffices to show that each one of these elements, z sub k, is in the center, because then some linear combination of them is also going to be in the center. And that's not so hard. You basically just kind of reverse this argument and you check that if you have one of these elements, then this will be satisfied, and so it'll be in the center. Okay. So maybe I'll just say, reversing the argument, shows that every element of the center looks like this. By which I mean it's a linear combination of these z sub k elements. Okay, now, in fact, these z sub k's, okay, so yeah, this is saying that the z sub k's form a basis for the center, actually. Right, because this is saying actually that they span. Right, this sentence is saying every element of the center is a linear combination of the z sub k's. Okay, so maybe I'll write, so the set of z sub k such that k is a conjugacy class. This set spans center. That's because of this. Every element of the center looks like this. But also they're linearly independent because like any two of these elements are just sums of basis elements of the group algebra that have disjoint supports. Like they're sums of just different like disjoint sets. And so just because the elements of, right, like, okay, maybe if I had some zk and I wrote it as like, I don't know, g1 plus, I don't know, maybe like g1 plus g2 plus g3, let's say there are three elements of this conjugacy class, and then like zk prime was like h1 plus h2 plus h3 plus h4 or something, and this is like some other conjugacy class with four things, just as an example. The point is that if these are different conjugacy classes, then these sets are disjoint, and so as elements of the group algebra, like this sum is linearly independent from the, or maybe I should say, okay, like all of them look like this, and so these disjoint sums have to be linearly independent. Maybe that example wasn't so illustrative, but hopefully this makes sense. Okay, so they are also linearly independent because they are sums of basis elements of the group algebra with disjoint supports. So they form a basis. Okay, and then finally, that means, okay, since these form a basis, like this set indexed by the conjugacy classes, they form a basis for the center. So the dimension of the center equals the number of conjugacy classes. Okay, so we kind of did a lot here. Maybe I'll just summarize what we did. So we wanted to show that the number of irreducible representations is equal to the dimension, we wanted to show that it's equal to the number of conjugacy classes. We knew already from a previous lecture that it's equal to the dimension of the center of the endomorphism algebra of the group algebra. This is also using the fact that every irreducible representation appears in the group algebra. And then we said, okay, we have this phi sub v construction showing that actually the endomorphism algebra is anti-isomorphic to the group algebra itself. So instead of having end of C bracket G, I could just write C bracket G. And then we said, okay, well now we need to understand what's the center of the group algebra. And then we found that actually the elements in the center of the group algebra are just these linear combinations of these Z sub k's, which are like indicator vectors of the conjugacy classes. And so they form a basis, so actually the dimension is equal to the number of conjugacy classes. Okay. Any questions up to here? Okay. Maybe I'll just state one other thing. Which is a corollary of this. The characters form an orthonormal basis of R of G. If you remember, R of G was the vector space of class functions. So these were the functions from the group to the complex numbers, which are constant on conjugacy classes. These formed a vector space, and we defined an inner product. And we already showed that they're orthonormal. Like we had a result at one point saying that if you take the inner product of two characters, then this is 0 if they are characters of the same irreducible. Sorry, if you take sorry, I missed something important. The characters of irreps of G. Maybe I'll look at the irreducible characters of G. Sorry, that's important. Irreducible characters of G form an orthonormal basis. So this is because we saw before that if you take the inner product of two irreducible characters, that if they are characters for the same irreducible representation, the inner product is 1, otherwise it's 0. So that gives you the orthonormal property and shows in particular that they're linearly independent. And then now we know that okay, wait, so now, okay, maybe I'll just say proof. We saw they are orthonormal in particular. They're linearly independent. Okay, so we just need to show that independent, that the number of them is equal to the dimension of this. Well, we've seen before that the dimension of this space is equal to the number of conjugacy classes, and that was because these indicator vectors of the conjugacy classes, which are these, something like this, those form a basis. So we already know, we saw that the dimension of this space equals number of conjugacy classes. Okay, but now we know that that's equal to the number of irreducible representations. So it's equal to the number of irreducible characters. So actually the number of these things is equal to the dimension, so they do form a basis. Number of irreducible characters is the dimension of R of G. Okay, so I guess one other thing I'll do. So I think we're finally getting to the end, hopefully, of the not combinatorics part. So I think next class we're going to do more representation theory with tensor products and I guess like induction and restriction of representations. And then I think maybe after that we'll get into the actual symmetric group, which will have permutations and stuff. Okay, but here's another theorem that's representation theory, just about finite groups. Maybe I'll do it over here. Okay, so earlier we had the character relations of the first kind. This is called the character relations of the second kind. Okay, so let's say we have two conjugacy classes, K and L. Then, if I take the sum over all irreducible characters, so I'll say sum over chi is an irreducible character of G, and I take the value that chi takes on K, which if you remember I was denoting like this, right? So this is just like chi is a class function, so it's constant on conjugacy classes, so this is just the one value that it takes on the elements of K. And then times chi L bar, the complex conjugate, this is equal to the size of the group divided by the size of K times the Kronecker delta sub KL. And again, this notation means that this is 0 if K and L are different, and it's 1 if K and L are the same. Okay? So in particular, if K and L are the same, then, well, this is also, right? So this whole thing is it's equal to the size of G divided by the size of the conjugacy class if these are the same conjugacy class, otherwise it's 0. Okay, so the proof. So okay, let's say we have two irreducible characters, say chi and psi are irreducible characters. Then we had the conjugates, or the character relations of the first kind. The character relations of the first kind state that if we take this inner product of chi with psi, this was 1 over the size of the group times the sum over the conjugacy classes K of the size of K times, okay, so this is just a way of writing what the inner product is. This isn't this is just sorry, a fact about how we can write this inner product by lumping things into conjugacy classes. But then we said this is equal to delta sub chi psi. Okay. So this was part of the character relations of the first kind. And the way you can think about this is this is doing some kind of, if you take the character table, this is doing some kind of inner product of the row corresponding to chi with the row corresponding to psi. And this is supposed to be some kind of inner product of the column for K and the column with L. So somehow we're going to try to relate this fact about inner products of rows in the character table to this fact about inner products of columns. Okay, so what this is telling us is that, okay, so let's define a modified character table. Define a modified character table whose entry in the, I'll say the chi-k position, okay, maybe I don't want, okay, whatever. The chi-k position is square root of the size of k divided by the size of the group times chi sub k. Okay, so all I'm saying is that the values in the character table, if you go to the row indexed by an irreducible character chi and the column indexed by a conjugacy class k, this is supposed to just be chi sub k, but now in the modified version we're going to multiply by the square root of the size of k over the size of g. So in this, this modified table has orthonormal rows. That's what this is saying because, yeah, I guess, okay, if you just write out this relation, but you rewrite it in terms of those, the new modified version is just saying that the inner product, like the usual inner product of two rows is 1 if they're the same row, and it's 0 if they're different rows. Okay? But then, so okay, there's sort of just a fact about unitary matrices. If you have a square matrix and the rows are orthonormal, then it has to be a unitary matrix. And if you have a unitary matrix, then its columns are also orthonormal. And that's exactly what we need. So, okay, it has orthonormal rows. Since it is square, so we're using the fact that the character table is square, which is coming from the theorem. Since it is square, it is a unitary matrix. So it also has orthonormal columns. It has orthonormal columns. And that's exactly what this is saying. Okay? Okay, how much time do we have? Okay, just a few minutes. Okay, I guess I can start on what we'll do next time. So I think there are only two sections left, or wait, yeah, two sections left. One is about tensor products, and the other one is about restriction and induction. And okay, you can kind of think of this as like ways of getting new representations from old ones. So maybe I'll start briefly saying something about the tensor product. So if you remember from group theory, if you have two groups, you can form their direct product. Okay, so given groups G and H, their product is the group G times H, and the elements of the product group are just, I mean, it's just the Cartesian product of G and H, like as sets, so they're just going to be ordered pairs, G comma H, such that G is in G, and H is in H. And the multiplication is just sort of the obvious thing. If you have an element G comma H and you want to multiply it by an element G prime comma H prime, you just multiply the first part G prime, then you multiply the second part H prime, and it's just that. Okay, so the question that we'll address next time is if we have a representation for G and we have a representation for H, how can we construct a representation for G cross H? This will be what's called the tensor product of the representation. And what we'll see is that actually all of the irreducible representations for G cross H are of this form. They're just obtained by taking an irreducible representation of G tensored with an irreducible representation of H. So what this is kind of saying is that if you ever have a direct product of two groups and you want to understand the representation theory, it just suffices to understand the representation theory of the individual groups by themselves, and then combining them is not very complicated. Okay, so yeah, I think that'll be it for today.